Hey, everybody. So we're going to continue with our look at confidence intervals. And as you might notice here, I've written we're going to do confidence intervals with sigma unknown. So in the previous videos, we had this situation where we had sigma was known. That's the population standard deviation, right? So we're trying to estimate mu, the population mean, but somehow we knew the population standard deviation. This is somewhat of an unrealistic situation because one of the ways in which we compute the population standard deviation is using the mean, and it just seems odd that we would have information about it. It can happen, but it's not the most typical situation, but it's a good place to start because it's our simplest confidence interval. So let's do an example where we don't know the standard deviation of the population and see what we can do with this lack of information, right? So let's start with this situation. Suppose we are working for some kind of consumer reports type magazine. So we want to look at products and make some valuations on them, right? Evaluate different characteristics that they might have. So for instance, let's say we are going to test some company claims that their light bulbs have an average of 1,000 hours lifetime, meaning they will on average stay lit for 1,000 hours, okay? So we might decide, well, why don't we go out and test ourselves and come up with a confidence interval for the mean. So we could go out and buy, let's say we test 38 bulbs. Okay, so we just go out, get 38 bulbs, plug them in, turn them on, see how long they last, and take the average. Okay, so we might find in our sample, so now this is our sample, that we have a sample mean of, let's say, 982 hours. Right? We don't know the population standard deviation, right? This isn't typical information to have around, that we know how the typical standard deviation for a population of light bulbs. However, we just took a sample, right? We have all the data, right? If we were the researchers in this, we would have all the data, how long each bulb lasted, here's our mean. We could compute the standard deviation. So suppose we did compute the sample standard deviation, S, and found it to be 75 hours. Okay, so that is remember our sample mean and sample standard deviation for these 38 light bulbs. Okay, and we want to use this information to find a 90% confidence interval. Okay, now remember all of our confidence intervals. We start with a point estimate, and then we're going to add and subtract error, right? All of them look this way, right? And the big difference is going to be, how do we compute this error, right? Our point estimate in this case is going to be X bar, and our error, well, if you recall the error from the previous one, we would take the standard deviation of the population and divide by the square root of the sample size. We're still going to do that with the sample standard deviation. Okay, 38. However, in the previous type of problem, we multiplied by the z-score associated to a 90% confidence interval. Here's the difference, okay? We have less information, right? In the previous examples, we knew the population standard deviation. So we're trying to estimate a population mean, and we know something about the population standard deviation. We have more information, right? Well, we don't have that information now, which means with less information, our estimate should be a little less good, right? It shouldn't be as precise or as close, right? Having less information typically makes us have less good estimates of things that are happening. So we're not going to use a normal distribution to compute a z-score. We're going to compute something called a t-score, right? So just like we would compute t of alpha or z of alpha over 2, we're going to compute t of alpha over 2, okay? This is t of alpha over 2 is our critical t-score, okay? It comes from a distribution, like a z-score comes from the standard normal distribution. This comes from a distribution called the student's t distribution, okay? We don't need to know much about it, okay? We're still going to do what we did for the normal distribution when we look for z-scores, right? There's a t distribution. It looks very much like a normal distribution. We'll take a look at it in just a second. We want a 90% confidence interval, meaning we want to find two t values between which 90% or 0.9 of the area exists. T alpha over 2, t alpha over 2, okay? And so we'll use a calculator to get this number just like we did with our normal distribution to find the z-score. So all we need to recognize is that we don't know the population standard deviation. And so in that case, we use the t-score and we go to a t-score calculator. And it's doing exactly the same thing for this distribution that looks very much like a normal distribution. Let's take a look at the two of them compared, and then we'll go to our calculator. So here is a picture. Let's move it away from all markings. Here is a picture. The blue line is the t distribution. The dotted line is a normal distribution. Notice that they have a similar shape, but there's more area away from the mean, right? If you look at the blue graph, the t distribution is missing all of this area in here, right? And it seems to have moved it further away from the center, right? It's a way of saying with less information, we don't get as close an approximation to the actual mean. Things are moved further out, okay? Now, some of this depends on how big our sample size is. Right now, I'm looking at a sample size of 2, okay? But, why is this happening? Okay, I don't know what just happened there. But as I increase my sample size, look what happens to the blue graph. It becomes closer and closer to the normal graph. So the t distribution, as our sample size goes up, looks more and more like a normal distribution, okay? So the t distribution, all we need to know about it, right? Remember with a normal distribution, we have to know the mean and the standard deviation. With a t distribution, they all have a mean of 0, and the only thing we need to know is the sample size. You might notice that this doesn't say slide to change the sample size. It says slide to change something called the degrees of freedom. Well, this is, the degrees of freedom is really just related to the sample size, at least in this case. That's not always what degrees of freedom are. But what we need to know are the degrees of freedom, which we'll call df, and it's just the sample size minus 1. Okay, so let's see now how we actually compute with this distribution. Okay. All right, there it is. So I've put in the degrees of freedom because we have a sample size of 38. So we take away 1 from this formula, n minus 1. I'm looking for a t-score. Look at this last spot down here, and I've put in, I want to find a t-score where the probability being below it is less than or equal to 0.95. That comes from this picture up here. Let me move it to where it's a little clearer. Notice we were looking for a 90% confidence interval, right? So there's 90% or 0.9 area right there. However, remember alpha is the confidence level subtracted from 1. So alpha is equal to 1 minus the confidence level. In this case, that's alpha is equal to 1 minus 0.9 or 0.10. That's how much area is left in these tails. Well, that means if there's 0.10 left in the tails, there's 0.05 in this lower tail. So now looking at this t-score here, the upper one, how much area is below it? There's this whole 90% plus this 5%. So there's 95% of area below it, right? So I'm asking this calculator to find the t-score with 37 degrees of freedom so that there's 95% of the area below it. And what we will find, for some reason this thing doesn't like, there it goes, maybe. Ah, it already did it. I'm still clicking, it already did. And we see a t-score of 1.687, okay? That is our t of alpha over 2, 1.687, okay? So now we can get to the business of computing our error. The error, let's get rid of, oops. Okay, let's get rid of these stray marks. All right, so we can get to computing our error now that we have our t-score. The error is equal to t of alpha over 2 times the standard deviation of the sample divided by the square root of the sample size. So in this case, it's 1.687 times, what did we say, 75. That was our standard deviation for the sample, divided by the square root of 38. And this came out to be an error of 20.5. And so now our confidence interval, our 90% confidence interval, and the way we usually state it is something like with 90% confidence, the mean lifetime of these bulbs is, and there's several ways we can write this next part. We could write 982 plus or minus 20.5 hours. I could use interval notation. If I take 982 minus 20.5, I get 961.5. And then if I add it, I get 1002.5, right? Saying that the mean is between these two numbers, or I could even write it as an inequality. Okay, any of these three is an acceptable way to write this down, right? Oops. The same information is contained in each of these, right? So I'm not saying to write down all three of these. I'm saying any three of these. There's the exact same information is contained in these three different sets of symbols, okay? So let's do one more thing. That's it for the confidence interval. So what I just want to point out is the similarities between the confidence intervals that we have so far. So we had case 1, where we are going to estimate the population mean and the standard deviation, sigma, the population standard deviation is known, right? And in that case, the error is equal to z of alpha over 2 times the standard deviation divided by the square root of n. Right? And then our confidence interval looks like this. Now we have case 2. We're going to estimate the mean. Sigma is unknown. And our error looks almost exactly the same, but instead we compute a t-score, and we're multiplying by the population standard deviation times the square divided by the square root of n, and we still compute our confidence interval by taking our point estimate plus or minus the error. Okay, and that is it. We will do one more type of confidence interval in a later video, and then we'll do a couple of examples where we have to choose between the three as we're deciding what to do. And we'll talk a little more about, there's a little more detail we're glossing over here, but we'll dig into those in some later videos. But I really want to stress how much the process is very, very similar. We just have to recognize which distribution we go to, the normal distribution or the student's t distribution. Okay, that is it for this one. Thanks, everybody. I will see you next time.